In this example, we'd like to solve a system of 3 linear congruences. So to do this, we need to use the version of the Chinese Remainder Theorem that's a little more in-depth here. So this one, first of all, let's write down everything we have. We have our A's. Our A1 is equal to 5. Our A2 is equal to 3. And our A3 is equal to 1. And then we have our N's. So these are our N's. So N1 is equal to 7. N2 is equal to 8. And N3 is equal to 9. From these N's, we have to create our capital N's. So capital N1, this is the product of the other two. Remember, that's how the capital N's are built. They're the product of all the other lowercase n's except for the one with the same index. So 9 times 8 is 72. Capital N2 is then the product of 9 times 7, which is 63. And capital N3 is the product of 7 times 8, which is 56. Okay, and so the last thing we need then, so by the way, at this point, we're not going to use this row other than that we need these numbers to compute stuff with the other numbers. But we also need our y1, our y2, and our y3. And so these are to be computed. And remember, the defining property of these y's is that y sub I times capital N sub I is congruent to 1 modulo lowercase n sub I. And here the I is 1, 2, or 3. The point is that these are all the same index when we use the capital N notation here. All right, and so that means that the y's are the multiplicative inverses of the capital N's modulo their corresponding lowercase n. So we can just look at each individual row here and we can find the y's. All right, so let's do this. This could be done by Bayes' theorem, but these numbers are small enough that we should be able to just see this pretty straightforwardly. So the first one is that y1 times 72 should be congruent to 1 mod 7. So this is for our I equal to 1. The first thing we can do is reduce 72 mod 7. So 72 reduces to 2 mod 7. So that means y1 times 2 should be congruent to 1 mod 7. And then so again, 7 is a small enough number that we can just do this in our head. What number times 2 is congruent to 1 mod 7? Well, 8 is congruent to 1 mod 7, and y1, therefore, is equal to 4. All right, because 4 times 2 is 8. 8 has a remainder of 1 when divided by 7. Okay, you could do Bayes' theorem on this if you want. I don't think it's necessary, though, when the numbers are small enough. It's almost easier to just do it by inspection. So now we need to do this for the other two, and so the next one says that y2 times 63 should be congruent to 1 mod 8. Same deal, we reduce 63 mod 8. 8 times 8 is 64, so this 63 can actually be replaced by a negative 1, congruent to 1 mod 8. So its remainder would be negative 1 if you go beyond and come back. And then, of course, negative 1 times negative 1 is equal to 1. So y2 we can use as negative 1. You could use positive 7 here if you want. Anything congruent to 7 mod 8 is acceptable for this y2. I'm going to use negative 1 because remember, we're going to multiply all these numbers together, the red times the pink or magenta times the blue. So by the way, we have 4 here, negative 1 here, and then we add these up. So we ignore this when we go across, but then we add up all the lines. So the last thing that we want to compute is y3 times 56 should be congruent to 1 mod 9. All right, and again, 9 times 6 is 54, so that's going to leave us with a 2 here. So y3 times 2 should be congruent to 1 mod 9, and then of course 2 times 5 is 10, so y3 should be 5. 10 has a remainder of 1 mod 9, so this is a 5. All right, so these computations over here of the y's, this is what we used Bayes' theorem on in the last two examples. Because these numbers are small enough, we didn't have to use Bayes on this one. So now we've got all of our ingredients. Our x is then congruent to the product. Remember, now at this point we ignore the green, the lowercase n's. We multiply straight across, add everything up, and then reduce modulo the product of all of these. So one thing we should say is that our capital N is 7 times 8 times 9, And if you multiply that out, you will get that this number is 504. Okay, and so when we multiply across here, we have 5 times 72 times 4 plus 3 times 63 times negative 1 plus 1 times 56 times 5. And this should all get reduced modulo 504. By the way, any number we get here is acceptable, but it's always good to have it reduced in the modulo space. And so I'm going to just write down what the answer is to this. So I added this up. I used a calculator. I know some of you are going to be surprised by that. But compute this out, you should get 1531. When you multiply all this out, modulo 504. And then 504 times 3 is 1512. So this will reduce. The remainder here then is going to be 1531 minus 1512. And 31 minus 12 is 19. So we end up with x is congruent to 19 modulo 504. And then it's pretty easy to check that 19 has a remainder of 5 when divided by 7. Check, that's good. 19 has a remainder of 3 when divided by 8. Check, that's good. And 19 has a remainder of 1 when divided by 9. So this checks out, and it was obtained by using the Chinese remainder theorem.